A bridge is a structure that can be constructed in 6 different categories, each with a different classification. These classifications include the type of material used, the different type of structural elements used, the load in which it is designed to carry, and whether the bridge has been fixed in position or is movable. A bridge is often thought to be a sophisticated, fundamentally designed structure. However, a tree or log that has collapsed over a creek can also be classified as a bridge. Although it hasn't been structurally designed to determine its load capacities, it still has the ability to allow travel from one side of the creek to the other. As previously mentioned, there are 6 different categories of bridges, and they include beam, truss, arch, cantilever, suspension, and cable stayed. Beam, arch, and suspension bridges are classified as rather basic bridge structures. It then gets more complex with truss bridges, and somewhere in between cable-stayed and cantilever bridges are located. There are times where cable-stayed bridges can be classified in their own category. However, there are also times where they are only a subclass of suspension bridges.
The bridge that was chosen by the group was a truss bridge. Both our first attempt and second attempt were both truss bridges. We all agreed that we did not want to overcomplicate the assignment and went for what we believed was a simple design. This bridge was also chosen because we thought it could hold the most weight, as it is the most commonly designed and used bridge. Through the use of equilateral triangles to disperse out the loads on the bridge, we thought that this would reduce the forces to only compression and tension. The 2 big beams at the bottom of the bridge, we believed that the forces would focus on the middle of the bridge, which became evident through both testings. In our first attempt, through our research, we decided to create 3 equilateral triangles with our truss bridge, but later through test results and more research, we decided that our first attempt was too small and the force of the weight wasn't focused on the middle of our bridge. So we extended our bridge and built 5 equilateral triangles, with a wider space in the middle of the bridge to place the weights, which we later learned was a wise choice as it held much more weight.
To begin construction of the first testing model, the group decided to use an I-beam approach as it was a shape that was used throughout construction. We did this with formations of 5, 4, 3, 2, 2, 3, 4, 5 to create the larger beams, which we used also in our final. And we also did a 3, 2, 2, 3 for our smaller beams, which we didn't unfortunately use at all due to their difficulty in manipulation. We replaced these with the circular beams. Circular beams were created of 16 strands of spaghetti in a circular formation, which we used for our testing bridge. And we noticed that they were too flimsy in the design, and so the first bridge failed for that reason. In the end, we changed them out for a more rectangular structure, which in formation was a 4x5 in spaghetti strands. The tested bridge was too short when we first tested, and so the final bridge was 45 centimeters at 8 centimeters wide. We also used 7 cross beams to connect the bridge frames to each other to complete the final product of the entire bridge being made of spaghetti and the super glue.
Prior to constructing the bridge, we had a look at a few designs and saw that the Pratt, Howe, and Warren truss designs were popular choices, especially when using spaghetti. We used Space Gas and engineering software to get a visual perspective on what we were about to construct, as well as the recommended software to allow us to recognize which beams predominantly the load was going to bear on. Truss bridges are known for their large load-bearing capacities, while also maintaining a simple design. As you can see, we as a group decided on a Warren bridge design. Our truss bridge spanned 350 millimeters, had a width of 80 millimeters, and a height of 150 millimeters. This bridge, along with the final bridge we made, was made up of only equilateral triangles. This is because although angles such as 30 degrees and 45 degrees excel better in different scenarios, Factoring in human error, 60-degree angles perform better as a whole and make up for a simpler design, minimizing mistakes. The test bridge weighed 174 grams, significantly under the required weight, and managed to load bear 9 kilograms. The problems we encountered, however, began with some communication errors as we built our bridge to the minimum specified length. This meant that when we were testing it, it did not span the whole distance properly, leaving us with some uncertainties, for example, weak points. However, we did come out with some bridge mounting load machine knowledge, giving us the ability to ensure the load was carried out over the main 2 I-beams as opposed to the 80mm smaller wide beams. For our final design, we made it 450mm long, giving us ample room to span across the full area. It was 80mm wide and 15mm tall. This change in the design gave us less weight to use on the I-beams, as we needed more trusses and other beams. This bridge was sturdy and weighed a perfect 200 grams. It managed a weight of 14.5 kilograms.
I told you.
Am I loosening it or what?
It's okay, just show me.
Am I doing anything?
Which one are we looking at?
The top.
It's at 10 now.
Say that.
Go slow, go. Oh.